So good evening everyone. Today I am going to present my presentation on Questa power aware simulation. So as we already know that the Questa Ultra comes along with HEP2. So we can work with the power aware simulation. So we can do simulations, that is we can do some low power stuff. So today I will be dealing with how to write a UPF file and what are the different low power strategies that we are going to use in order to reduce our power during synthesis stage. But initially we are going to decide our power planning at RTL stage. So for today we have the agenda of writing UPF file and also simulating the same with the necessary code as well as test bench. Why we have to go for low power? This is a constant question that has been asked by everyone. Why we have to make our designs use less power? Because first, the primary reason is we have to save the power of the SoC chip. That is, for example, you have a very complicated ASIC chip. So what you want to do is you want to reduce the power to such an extent that it will not dissipate any heat, so that your applications will work better. So ultimately what you want to do is you have to reduce the resources that are natural resources that are getting wasted because we are using up extra power. So instead of using the power, we are indirectly contributing to different pollutions, say air pollution or water pollution, n number of pollution sources that we are going to indirectly contribute. So that's why we are going for low power. If you are going for low power, we can cut down all the costs of generating the power. So indirectly we will be contributing to reduction in pollution in one way or the other. So why especially now I am dealing with power aware simulation is the fact that at the initial stage of the design itself, we should be able to decide what will our power be. Say for example, if you go for an ASIC flow, first you will start with your architecture or your specification sheet. From the specification sheet you will decide so what are the tools you are going to use and what are the steps that you need to follow to get a JDS2 file. That is the ultimate final output for fabricating any ASIC chip. So first we start off with RTL design. Maybe we'll choose VHDL or we'll choose Verilog. So then we move forward for verification. So verification is a tedious process. Nowadays it's getting complicated because we are in the era of nanometer level. That is, we are currently using 14 nanometer or 10 nanometer. Still the research is going on. So currently in the industry we are using 65 nanometer or 28 nanometer. Even the chips, FPGA chips or an ASIC chips have been manufactured with certain applications with 28 nanometer design technology node. So as you already see that in the technology flow we have started from 180 nanometer, say 180 nanometer to 130 nanometer we have migrated, from 130 nanometer to next 90 nanometer, and from 90 to 65, 65 to 45, 45 to other lower nodes. So one distinct comparison you can see is that when you are moving from 180 nanometer to 130 nanometer, there is a scale down of 1 by root 2. You can see the factor. So 180 to 130 the scaling is 1 by root 2, and 130 to 90 again the scaling is 1 by root 2 times, and between alternate technologies, that is 180 and 90, you have a scaling of 1 by 2. So every technology that is shrinking, it is shrinking by approximately 1 by root 2 times. So that is the reason we have to estimate in future after 14 or 10 nanometer what is the nanometer technology that we are going to use and how efficiently can we work with ASIC chips. So that is the main criteria of going for low power and dealing with ASIC applications. And next, one more thing is I want to stress on is up till 180 nanometer we are not doing much of low power because the main thing is the designs were not so complicated. But when you are going for 65 nanometer and below, as you can see in the graph, that the complexity or the need for low power has been increased. So that is the reason we are going for low power, and the target for this is the different applications like mobile applications, communications, or any consumer goods that we are using in day-to-day life. So the fact that we have the need, that's why we are going for low power. So here previously before 180 nanometer technology, only we used to have dominated switching power, but we have now static leakage power also. That is why the need for low power is being enhanced, and we have to tackle in such a way that we need to meet our power requirements by specific applications that is being demanded. So in this regard, for going for a power aware simulation, we need to have certain standards. Standards in the sense, what is the format that we are going to use, or what is the file, or what is the thing that we are going to do for our design to meet the architecture level, or you can say for any design, for particular design we want to reduce the power. So the format is unified power format. So this is the standard IEEE format that is being adopted by number of semiconductor companies. There is also other format CPF, but only 20% of the industry is being currently used CPF, whereas 80% of the industry is currently they are in favor of UPF. And CPF is common power format from Cadence, but UPF, there are number of vendors that have come forward and developed this standard. So Mentor Graphics is one of them, which has currently been focused on UPF standard. So what is the thing? What is exactly UPF, and what we are going to do with this UPF file? It provides the ability for electronic systems to be designed with power as well as key considerations early in the process. That is, generally what we are thinking is, we are initially writing our code, then we are going to synthesize. After synthesis, we are going to we are going to implement some low power techniques. That is the general trend in ASIC design. But the trend has been broken since 65 nanometer technology node, and we have to tackle the power criteria before the synthesis itself. That is why UPF plays an important role before the synthesis to tackle such low power considerations. So why you want to go for UPF? As I already told, it's been developed by various companies, and one of them is Mentor Graphics. So it is very popular across industry. And one more thing is, it supports vendor specific formats and creates opportunities for checking the bugs, and we can fix the timing also after doing your low power stuff. And if you have any inconsistent specification, we can find out and we can debug. So where is UPF used? Where exactly are we dealing with UPF now? As you can see here, UPF, we have UPF at number of phases. The first phase comes at the RTL level, and then next comes during synthesis level, and next during place and route. So as you can see that during the RTL level or during the synthesis level, during the place and route level, we have to specify the supported UPF formats, and we can do equivalence checking. That is, logical equivalence checking is nothing but comparison between an RTL and a netlist. It could be RTL versus RTL, or netlist versus netlist, or RTL versus netlist, and netlist versus netlist. So what is the thing with logical equivalence checking is that, so before your design, you have the RTL. You would have specified with respect to specifications, you would have designed your circuit, or you would have written it in VHDL or Verilog. So after the synthesis, you are going to get a netlist that is optimized with or without low power constraints. So now we have to check whether your netlist matches your RTL or not. So why we have to do all this stuff? Because basically you want your design to work according to your specification. Since you have already written RTL with respect to specification, we have to ensure that our netlist is same as a specification. Unless or until your netlist is not same as specification, you can never tell that particular application will work. So that is why we have to do equivalence checking, and with UPF we can move forward for equivalence checking. That is by providing UPF during the RTL phase as well as during the synthesis phase. If you are providing the UPF file, we can generate the netlist accordingly and compare both golden netlist, that is the netlist golden netlist is nothing but the RTL code, and revised netlist is nothing but the netlist that is generated from after synthesis. So what are the basic steps in doing power aware simulation? First, we have to build a power architecture. That is, what is the plan that you are going to do to implement in your design. Then you have to create a strategy. What are the low power techniques that you are going to use? The third and the final step is we have to set up or write a UPF file, and we have to map accordingly what your power specifications are. What the Mentor Graphics solutions exactly provide for the same flow. So we have Questa Ultra, as I already specified, for power aware simulation, and for equivalence checking we have Formal Pro. So Mentor Graphics provides a Formal Pro software that does RTL to RTL, netlist to netlist, and RTL to netlist equivalence checking. So during the place and route stage also we can provide the UPF, so that we can initiate and check out whether our design actually meets the specifications or not. As I already told, we can you can do the UPF, or we can implement the low power strategy at RTL or during the gate verification itself. So what the low power design intent, that is what you are going to do, how you are going to implement is, the different techniques are power gating, retention cells, and isolation flops. And during the formal flow, we are Formal Pro with the software, we are going to just check out whether our generated netlist is same as the one in the RTL. So these are the tools that have been supported from Mentor Graphics. Isolation cell. So what is the role of isolation cell in a typical low power? So first let us consider that we have a certain design, and we have number of power domains. Power domains are nothing but every domain is going to work in different voltage. So you have, say, you have a FIFO, you have an SRAM, you have a MUX. There are three, four blocks in your design, in your hierarchy, and you have you have each block working at different voltages. Say one block will be working at 1.8 volts, or another block will be working at 1 volt. That is based on the specification. So now let us talk about isolation cells. So isolation cells is nothing but it is going to isolate your input and output from the powered down blocks. That is, whenever we have created a power domain, we have to shut down the blocks, because if they are not in use, we have to shut down the blocks, and then we have to prevent the unwanted or don't care states to prevent it from propagating to next block. So in this regard, so in the don't care state, what we are going to do is, so we are going to prevent these don't care states from propagating to further blocks. So we have to use a strategy called isolation cells. So there are some certain cells in the libraries that we can use, and we can make the signals and clamp it to either value 0 or value 1. So as you can see in the diagram, that here is a typical AND gate, and for isolation cell, this is, they have clamped to value of 1. So whenever you are isolating this block from this block, say for example this block is blocked now, that is, it is powered down. So the output of this is unknown. So the don't care will be propagating to next block if we don't have the isolation. Now with isolation, this is gated. So the isolation, the ISO signal controls what signals to be sent to next block. So in that way we are going to optimize, or we are going to do our low power in this way. That is, during the shut off mode, our block will be powered down. So as a result, we are going to gain some power, or we are going to save some power, and the correct output will be propagated without any unwanted signal. So that is the thing with isolation cells. So the next comes is retention flops. So you told me that we are going to send some specified value like 0 or 1 from the previous power down state, because propagating a don't care will again arise number of issues, like what will be the timing violation, or what will be the logical state, whether our design is going to work as per the specification or not. So we have to have a clear input and output specification. So with respect to the retention flops, as you already see in this register, in this flop, or we can say, what is the thing with retention flop is that we have save and restore. save and restore signals as an input. That is, whenever we are going to shut down any PD block, or we can say power down block, we have to save the current state of that particular block. Say for example FIFO. FIFO, there will be some inputs and some outputs that is being coming out of a block. So we have to save that states. So where we are going to save that state? We are going to save the state is in any flip-flop. So that is a retention flop. So if we are saving certain inputs or output values in flip-flop, then it is a retention flop. And we are going to restore the same value after the block has been powered up. So here you can see an example of a typical application. So in that we can see power controller, transmitter, receiver and a checker. So here we have demonstrated all the components here. So here you can see that the transmitter works with 1.08 volts and the receiver is going to work with 0.864 volts and the checker is going to work with 1.08 volts. Here you can see that two blocks are going to work with same voltage, but whereas the receiver blocks need lesser voltage. So as a result, we have to have some control over what we are going to do and how we are going to decide the power plan. So the basic plan is, first we are going to set up power domain for each block. So for transmitter we have a power domain called TX_AON, and for receiver we are going to have a power domain, and for a CRC also we are going to have a power domain. Now we are having all the power domains. What is the next step that is needed to be done? The next step is we have to have the compatibility between each block. Although the signals are directly connected, if you are thinking at the final stage, what we want is, we don't want the 1.08 volts to be propagated to the receiver, because the receiver just requires 0.864 volts. So as a result, we want a level shifter. Level shifter is nothing but we are going to downgrade the voltage or upgrade the voltage based on the specification. So level shifter plays a crucial role in connecting between two power down or two blocks, or you can say two power domains. In that way, our level shifter is going to help us in deciding the power plan. So let us come to Questa power aware simulation verification flow. So what we are going to do in this is, first we are having our RTL code and we are having our test bench and we have a few power aware models. So along with UPF and library files, we are going to compile and we are going to optimize the same. So along with the UPF file, we are going to check out like what will be the output of the design and whether we are able to achieve some power reduction. That is, during the simulation stage, we can take a look in the designing part or architecture, like whether certain signals have been shut down or certain signals have not been used, and which block is going to be in the on state or off state. So all those things will be taken care here. And during the simulation stage, we are going to get the output, like what will be our final result with respect to isolation cells, retention flops and level shifters, and how they are influencing our design to work. So I have chosen here a typical UPF example. So this is an example where we have two clocks and it propagates to a mux, or we have a mux and it will select clock 1 or clock 2, which is both are working at different frequencies. Then it is going to LFSR, it is linear feedback shift register. From there we have a sequence detector that will detect the sequence of LFSR output. That is, LFSR output is, we are not going to get in the same order, we are going to get in a different manner according to the Boolean equations that we are going to mention. So what is the order of the equation, all those things has to be taken care. From there, after the sequential detector, a counter is present where it will detect how many similar patterns are going to occur. From there, since the value will be coming in hexadecimal, I will be converting that to BCD converter, and finally we will check how many patterns have been detected based on the input of the clock. Either we are selecting clock 1 or clock 2, and we have a reset signal over here which will clear all the states and reset to the default values. So these are the blocks. that the example I am going to show. What is my power plan, or what is my architecture that I am going to use for, or what is the UPF file that I am going to write? How am I going to write that? So here you can see that we have 5 domains: domain 1, domain 2, domain 3, domain 4, and domain 5, each with for one block. And you can see the top domain, which is enclosed within the 5 domains, and mux is in one domain, and all others are there in individual domain. And the same thing, if you want to convey, or if you want to write the same thing in a UPF file, you can use UPF standard command like create underscore power underscore domain top underscore PD, that is top power domain. That is the topmost power domain that is being written. And next, create underscore power domain clock underscore mux underscore PD minus element CM. You have to mention the what is the instantiation name that you are going to use in your test bench. Accordingly, you have to mention the same thing. Same thing follows for all the power domains. In this way, we can create the power domain for individual blocks. So already I have discussed, like we have to create five power domains. Step in the writing a UPF file is we have to create ports. So as you can see here, it is in the red color port in the top domain, the topmost domain. You have 2 ports here. One for both of them, we are going to use a command called create underscore supply underscore port VDD underscore port. So now this one is a VDD port for the top module, and this is the VSS port for the top module itself. After the port, we have to generate, or we have to create a net, supply net, that is VDD rail. So VDD rail is common for all the VSS for each and every block, and we have similarly VDD rail is not common, VDD rail is separate, and VSS rail is common to all the power blocks. Similarly, we have to create the supply net for each and every power domain. Here you can see that V clock mux, VLFSR, VSD, V count, and VBCD. For each and every one of them, we have to create a net, and we have to connect this net to the supply net. So for connection, we are going to use a command connect underscore supply underscore net. Say for example, if you have a fourth one, VSS4, we are going to connect it to VDD port. So in that way, we can have a logical connection between the two. Set underscore domain underscore supply net. So we have to set the supply net. So for that, this is the command that we are going to use, and we are going to connect our VDD rail and VSS rail accordingly. So this I have shown for a typical clock, the connections. So why do we require power switches is to have the controllability over our low power design or low power architecture, that what we are going to do. So here, this is our power switch that for the total all the power domains that I have specified here. So here you can see the ports for each and every domain. So this is the output port for each and every domain, and this is the input port, and this is the control port. So accordingly, if you are taking up an example, so let us take here in detail, we will discuss about how we are going to plan, or how we are going to write the UPF file with a simple mux power domain. So if you are considering domain 1, it has 2 inputs, clock and clock 2, clock 1 and clock 2, and we have an input port of V in 1 and an input net of VDD rail. That is, VDD rail is connected to the VDD port from here. So, and then this port will be connected to the switch, and we are going to have another port here, control signal. Control signal is going to be again connected to the switch, and based on the control of these 2 signals, we are going to get an output, and the name of the output net is V clock mux, and the output port is V out 1, and the net name for the control signal is clock mux switch control. So here, in order to get this, or in order to achieve this, the command that we are going to use from the UPF file is create underscore power underscore switch, any name, that is clock underscore mux underscore switch, and minus domain. Since the domain I have specified is the domain name of the clock mux, that is clock underscore mux underscore PD, and input supply port, that is Vin. So we have here, and VDD rail. VDD rail is a thing that we are going to connect initially. Then output supply port, that is V out 1. That is the port that we are going to connect. And what is the net name we have to mention is V clock mux. and the control port similarly what is the port name as well as the net name we are going to mention. And since the topmost portion, that is up till control port, we have a clarity over how we have to write the UPF code. But whereas why I have mentioned this on state, off state, that is we know that any power domain we are creating, the sole purpose of the power domain is to be shut off or shut on. So to turn off, to turn on, what is the criteria that we require, or what is the Boolean expression, or what is the condition that we want so that our state will be in on state. So we have written the command like on underscore state clock mux on. So if the Vin, that is control signal, is equal to 0, if the control signal is equal to 0, then we are going to turn on, that is turn on the power domain. To turn off, the control signal should be 1. So if these conditions are satisfied, our power domain will be turned on and off. So we can say that we have a control over the control signal. So whatever we are going to specify in the control block or control signal, control port, we can control the power domain here. So similarly we can do for each and every domain, domain 2, 3, 4 and 5. We can, as you can see in the diagram, that each has an input port, each has a control port, each has an output port, and each has a net name that is being assigned. The same thing we are going to implement for all the 5 power domains. So why we have to go for isolation strategy first of all is, as you can see that, take one example of a power domain 1. So we have mux here, and we are going to get inputs from clock 1 and clock 2. So now we have to isolate the signals, that is input and output, from the previous block. In case there is any previous block which is powered down, we have to prevent unwanted state or a don't care state to propagate it to next block. So if it propagates, unwanted transitions is going to happen. Ultimately the transitional power will be increasing as well as static power will be increasing. Because of that, your architecture or a power that your circuit or an SOC is going to consume, it will rise up. So as a result, we have to tackle this don't care condition. To tackle this don't care condition, we are going to use isolation strategy or isolation cells. So by using isolation cells, we can control the output that is going to be sent to next block. So in that way we are clamping any value to either 0 or 1. So here you can see the corresponding UPF command is set underscore isolation. So this is the name of the strategy that I am going to give. So you can give any name and the domain, which domain you want to implement. So clock underscore mux underscore PD, that is the domain 1 I am going to implement my strategy. So what is the isolation power net? That is VDD rail. And isolation ground net, that is VSS rail. Here you can see isolation power net and ground net. And clamp 1 means the output is going to be 1 irrespective of if the previous domain is shut down and any don't care signal propagates. So we can modify accordingly based on the specifications of the design whether the clamp value has to be 1 or 0, whether it applies to inputs or whether it applies to outputs. Generally, isolation strategies are applied to the output for any block, for any power down blocks, because ultimately we are going to get the don't care state only at the output juncture. Sometimes we are going to use the isolation strategy at the input to prevent any unwanted transitions that are going to occur in the previous block. So in that way we are going to control. So this is the command that we are going to use for a typical isolation strategy. So now we dealt with how to tackle a don't care condition. So we are going to send a clamped value across the output. So what is going to happen to the current state of the block after the power domain? I mean power is downgraded or switched off for the previous block. Because the previous block has already been switched off, we have to know what is the output if we would have got, if it is turned on. That is, the state would have been in the constant because of the low power strategy that we are going to use. That is, say for example, let us take this simple example, counter. So previous to counter, say we have mux here. If the mux has been powered down, we know that the output will be don't care, but isolation cell is going to prevent the output to be propagating to counter, and we are going to clamp it to value 1. So the input of counter will be 1. But what is the value of the output if we would have not used isolation strategy? That is, we have to save the output of the previous block, previous power domain block. So that is why we are going to use retention strategy. So retention flip-flops are going to be used if and only if we have some certain power domain strategies wherein we have to store the inputs or outputs current state. So we are going to store the values of inputs or outputs in this retention flip-flops, and then we will restore the same value after the block has been powered. So this is a good way of storing the result, because if you are losing any part of the input that you are going to get, ultimately the desired program what we want is number of patterns that have been detected. We are going to get the wrong number of patterns. So because of that, we have to store the result. So retention flop is a good strategy. In order to write the same thing in a UPF file, we can go for _retention, and what is the name of the strategy, that is any name you can use for convention, RET_strategy4, and which domain you are going to apply for. So it is counter_PD power domain, and what is the retention power net, and which is VDD rail, and the retention ground net, that is VSS rail, that is common for across all the blocks. And then what is the control signal, and what is the condition at which we are going to save the signal, that is whether the save count will be high, whether the restore count, what should be the value. So all those things we are going to monitor. And minus restore_signal we have here. So whenever we are going to restore, this flag will be enabled high in order to know that we have started our restoring process. And we have to map, because during the architecture phase we cannot get like which flip-flop is going to be used by our design, because in the library there will be n number of flip-flops that are going to be present. Each will be having its own characteristics. There is a specific isolation flip-flop that should be used in order to store these values. This can be done at the gate level simulation stage. So then we are going to mention here. Here you can see that default I have mentioned the lib_cell_name. Say for example your isolation strategy is isolation cell name is ISO_ABCD or something like that. So you have to mention the name from, you have to browse the library file and you have to mention the same name here. Only then you can go forward for power aware simulation. So now finally what I have to show is final result what has been done for the complete example. So here you can see that we are using 2 clocks of different frequencies, and this is a clock select. It selects either clock 1 or clock 2, and then we have different control signals here, and then we have the isolation strategy, isolation cells for all this, isolation 1, 2, 3, 4, 5, and we have save and restore. So we'll be here you can see that I have written a test bench in such a way that isolation 4 will be powered down. So you can see that when isolation 4, the signal changes from default don't care condition to value 1. That is, the isolation strategy has been started. Before going into isolation, as I already told, retention flop has to save the state. So for that, we have here save count. So here our count will be saved here. So before shutting off the block, our output of the particular block is been saved, that is counter block has been saved. And then next, after a certain point of time, here you can see that based on the control, we have a certain control in our command. So based on the control signal, again we are telling the block that we want to have our previous state to be loaded back. So we have initiated a restore condition. So here we have a save condition, here we have restore condition. That's why the restore signal has been enabled and it is made 0. Then after that, the isolation is powered domain, so all the blocks are going to work normally accordingly. So this concludes the power aware simulation. So the main focus is on low power strategy. At the architecture level, we have to plan our what we are going to implement, and power plan is essential at RTL level, gate level, during the physical design also. And the importance of UPF or unified power format in the context of low power designs. UPF plays a crucial role in deciding our power architecture as well as your ultimate power of an SoC chip. Thank you.